You are welcome once again to today's tutorial on another type of AM modulators. And in this case, we are going to focus on single sideband suppressed carrier modulator. In my previous tutorial, I talked about the double sideband suppressed carrier modulation. As we observed, I made a sketch, which is the phasor diagram of a double sideband. And this was the suppressed carrier, and this was the upper and the lower sideband, which is FC plus FM, and then FC minus FM. This is the amplitude. So this is the lower sideband, and this is the upper sideband. So basically, as you can see, it has two sidebands, the lower and the upper sidebands, which is the double sideband suppressed carrier. We came into conclusion that both the lower sideband and then the upper sideband has the same information. And therefore, if they have the same information, we can decide to transmit one instead of transmitting all the two. Because at the end of the day, we require power to transmit both sidebands. In doing this, we can decide to suppress either the low sideband or the high sideband. And therefore, at the end of the day, we are going to have a resultant as FC plus FM. FC, yes, FC. The dotted line shows that those lines have been suppressed. And as you can see, this is the lower sideband, this is the upper sideband. The lower sideband, along with the carrier sideband, has been, or the double sideband has been suppressed, while leaving the upper sideband. You can also decide to suppress the upper sideband, and then you leave the lower sideband. So in the case whereby you suppress the upper sideband and then leave the lower sideband, it's also acceptable. And at the end of the day, when you are drawing it or you are considering one, you can do it like something like this, or if you want to represent like a rectangle, like when we did earlier on, you can get something like this. FC plus FM, FC minus FM, and here's FC. Here it's USB, and here it's LSB. So for this one, we have decided to suppress the lower sideband along with the single sideband system, which mostly transmit a single sideband, has a higher power. And as a result, the power allocated for both the carrier and the other sideband, which has been suppressed, will be added in transmitting that single sideband. So what I mean is that if I want to transmit this upper sideband, this power that I needed to transmit for this lower sideband, together with the power that I need to transmit for the carrier sideband, will be added to the power that I need to transmit the upper sideband, so that I'll get a very big power, and then I'll do my transmission. So let's move on and do a mathematical analysis for that. Now, for this type of modulation, as I said, it's made up of two sidebands, either the lower sidebands and then the upper sidebands. And in doing modulation, I always say that we need two signals, which is the M of t. This is equal to AM cos omega mt, and then my carrier signal, which is AC cos omega ct. When I have this, I'll be able to modulate the signal. Let's think of it. What type of modulator mostly give us both sideband? This is DSBS. And therefore, in doing the DSBS, you'll be able to have a one sideband, and you will talk about how you'll be able to generate a single sideband using its own technique. So at the end of the day, the resultant equation or wave that you are going to get is equal to AM AC over 2 cos omega c plus omega m or t or S of t equal to AM AC over 2 cos omega c minus omega m or t. These are the various sidebands that we generated when we were doing SSBSC modulation. So for a single sideband, it's either S of t equal to this one or X of t equal to this one. Looking at it, you can see that if we are looking for the bandwidth, it's going to be FM. This is the reason. Now we don't have two sidebands in order to subtract the upper sideband from the lower sideband. As a result, if from SSBSC my bandwidth is equal to 2 FM, now I'm having a single sideband. What do you think it will be? This bandwidth divided by 2 will give us 2 FM divided by 2 will give us FM. Therefore, the bandwidth for a single sideband suppressed carrier XXBXC is equal to FM. This is the bandwidth of it. And this is equal to the frequency of the message signal or the modulating signal. The same applies to the power of the single sideband suppressed carrier wave. Let's assume that we are picking the upper sideband. That's what we desire to get. And therefore, my S of t is equal to AM AC over 2 cos omega c plus omega m t. As we did earlier on in one of my videos, power is equal to IV and it's equal to V squared over R. And we came up to know that we are going to get V squared over 2R. And therefore, what is my amplitude? My amplitude V is equal to AM AC over 2. So in substituting it into this power equation, we are going to get power is equal to AM AC over 2 all squared over 2R. And at the end, we are going to get AM squared AC squared over 8R. So this is the power requirement of a single sideband suppressed carrier. And therefore, if you are looking at the lower sideband, this one, I use the upper sideband for the calculation. So when you are using the lower sideband, it also has the same power, AC squared, AM squared, or over 8R. When the R is not being given, you take R to be equal to 1 during your calculations. That's 1 ohm. Therefore, the total power P of T is equal to the power of the lower sideband, and also R is equal to the power of the upper sideband, depending on whether you suppressed the upper sideband and you took the lower sideband, or you suppressed the lower sideband and you took the upper sideband. Let's quickly look at some few advantages of the single sideband suppressed carrier. The first one, I will say that to make transmission of more number of signals to be allowed, we save more power as well, because for one sideband, we need only that power to calculate it or transmit it. So for power saving. 2, it allows transmission of more number of signals. And then 3, we can transmit higher power signals. As I was saying, as we save power, we can also know that if you are transmitting higher power signals, the other ones that have been suppressed power can be added up to help us transmit those signals. It also helps to present less amount of noise in whatever we are doing. Let's say less amount of noise. And then lastly, what I will use is that it helps us in less likely to occur. Let's say it helps us in signal not fading. So during transmission, less likely for signal to fade. During transmission. Let's look at some few disadvantages. The first disadvantage that I will talk about is that the quality of the signal will be affected. The quality is being affected. We can help to prevent this by using a transmitter and receiver that have an excellent frequency stability. So if you are using such transmitters that have an excellent frequency stability, we'll be able to improve the quality of a signal produced by a single sideband suppressed carrier. And the second one is that it's a complex process. So what I would say is that the way of generating a single sideband suppressed carrier is really complex, which is one of the disadvantages of single sideband suppressed carrier modulation. Let's quickly look at few applications. For one, for power saving requirements and low bandwidth requirements. So if you are transmitting something that requires a low bandwidth and also for power saving, we use single sideband suppressed carrier. It also helps us in radio communication. In television, and many others, and even in military communications, they are being used over there. So now that we understand a single sideband modulation, I would like to end this tutorial here. And in my next tutorial, we will talk about a single sideband suppressed carrier demodulator. Thank you for watching and see you in my next video.